Hey everyone, welcome back to Chem Story. Today, we're diving into a really important concept in organic chemistry, alkane conformations and how their energy levels change. Have you ever wondered why some molecular shapes are more stable than others? Or why one conformation feels more strained than another? Well, that's exactly what we're going to break down today. We'll take a closer look at the conformations of ethane, propane, and butane and see how things like torsional strain and steric interactions affect their stability. Let's get started. Let's start with ethane, the simplest alkane to visualize using a Newman projection. Picture this. You're looking straight down a carbon-carbon bond, with one carbon in front and the other directly behind it. This gives us a clear view of how the hydrogen atoms are arranged and how that arrangement affects the molecule stability. In the diagram, the front carbon's CH bonds stay fixed, while the rear carbon's CH bonds rotate in 60-degree increments. As we rotate the rear carbon, the dihedral angle between the front and back hydrogen atoms changes, moving through a full 360-degree cycle. At 0 degrees, the molecule is in an eclipsed conformation. That's when the hydrogen atoms on the front and rear carbons are lined up directly. This alignment causes electron clouds to get too close, increasing torsional strain, and that pushes the molecule's energy up. But when we rotate to 60 degrees, the molecule moves into a staggered conformation where the hydrogen atoms are offset from each other. That reduces electron repulsion, lowers torsional strain, and makes the conformation more stable. As we keep rotating, the molecule keeps alternating between staggered and eclipsed conformations. And by watching these changes, we can clearly see why some shapes are more stable than others. In the eclipse conformation, the hydrogen atoms line up directly with each other, and that maximizes electron repulsion. This extra torsional strain raises the molecule's energy, which makes the conformation less stable overall. Now, in the staggered conformation, the hydrogen atoms are spread out as far apart as possible. That spacing helps minimize electron repulsion, which means less torsional strain, and the molecule becomes much more stable. But why is the eclipsed conformation higher in energy than the staggered one? Well, there are two key reasons: electron repulsion and hyperconjugation. First, in the eclipsed conformation, the CH bonds on neighboring carbons line up, and that puts their bonding electrons way too close together. Since electrons are negatively charged, that closeness leads to strong repulsion, which creates torsional strain and raises the energy of the molecule. The closer the electrons are, the more they repel, and that makes the eclipsed conformation less stable. Second, there's something called hyperconjugation that helps stabilize the staggered conformation. It happens when the bonding electrons in a CH bond on the front carbon can partially delocalize into the antibonding sigma orbital of a CH bond on the rear carbon. That interaction helps lower the energy of the molecule. But in the eclipsed conformation, those orbitals don't line up the right way, so the stabilizing effect of hyperconjugation is lost. Out of the two, electron repulsion is the main reason for the energy difference, while loss of hyperconjugation adds a smaller, secondary effect. Put them together, and you've got a clear reason why molecules naturally prefer the staggered conformation whenever they can. Now keep in mind, torsional strain and steric strain are two different things. Torsional strain happens when bonding electrons repel each other because the bonds are lined up, like in the eclipsed conformation. It's all about electron repulsion between bonds that are too close. Steric strain, on the other hand, is more about size. It shows up when atoms or groups physically crowd each other, especially if they're bulky and don't have enough room to spread out. In the case of ethane, we're only dealing with small hydrogen atoms, so there's no real steric hindrance to worry about. That means the instability we see in the eclipsed conformation comes entirely from torsional strain, not from steric strain. If we look at the energy difference between these conformations, the staggered form is about 12 kilojoules per mole more stable than the eclipsed form. That means, under normal conditions, ethane molecules almost always prefer the staggered conformation because it gives them the lowest energy and the most stable structure. Let's take a look at the energy graph of ethane as we rotate the rear carbon from 0 to 360 degrees. The y-axis shows energy in kilojoules per mole, and the x-axis tracks the dihedral angle as the molecule rotates. The graph follows a repeating pattern, with peaks at 0 degrees, 120 degrees, and 240 degrees, These are the points where the molecule is in an eclipsed conformation, experiencing the most torsional strain. So naturally, these are the highest energy points. In between, we see valleys at 60 degrees, 180 degrees, and 300 degrees, and those represent the staggered conformations, where the bonds are offset, electron repulsion is minimized, and the molecule is more stable. This trend makes it super clear. Staggered conformations are always lower in energy, while eclipsed conformations are higher because of torsional strain. And that's exactly why Ethane naturally prefers the staggered conformation. Now, let's move on to propane. At first glance, it behaves almost exactly like Ethane when it comes to conformations. We still see staggered and eclipsed forms, and the molecule still rotates the rear carbon in 60-degree increments. But here's the key difference. One of the hydrogen atoms on the front carbon is replaced by a methyl group. That's a CH3. And that one change introduces a new factor that affects the energy difference between conformations. In propane's eclipsed conformation, the energy is a little higher than in Ethane, and that's because of the methyl group, or CH3. In Ethane, all we have are CH and CH interactions, but in propane, the eclipse form brings in a new interaction between a CH bond and a CCH3 bond. Since the methyl group is bulkier and has more electron density than a hydrogen atom, the repulsion between bonding electrons goes up. That extra crowding makes the eclipsed conformation in propane even less stable than it is in Ethane. In the staggered conformation, the methyl group and the hydrogen atoms are spread out as far apart as possible, and that helps reduce torsional strain. Just like in Ethane, this is the most stable conformation, because electron repulsion is at its lowest in this arrangement. In the eclipsed conformation, the total energy is around 14 kilojoules per mole, a bit higher than Ethane's 12 kilojoules per mole. This increase comes from the CH and CCH3 eclipsed interaction, which adds extra torsional strain to the molecule. Since the methyl group is bulkier than a hydrogen atom, the electron repulsion is stronger, and that makes this conformation even less stable than what we see in Ethane. In the staggered conformation, the energy is at its lowest because repulsion is minimized. Just like in Ethane, the staggered form is still the most stable. The overall trend stays the same. Staggered is stable, eclipsed is strained. Looking at the energy graph of propane, we can see this trend even more clearly. Just like in Ethane, the graph shows peaks at eclipsed conformations and valleys at staggered ones. But this time, the energy difference is just a little bigger. It really highlights how even a single methyl group can affect molecular stability. And this effect? It gets even stronger in larger alkanes, like butane. Next, let's take a look at butane. So far, in both Ethane and propane, we've seen the same general trend. Staggered conformations are always more stable, and eclipsed conformations have higher energy because of torsional strain. Butane follows those same basic rules, but there's one big difference. Instead of just one methyl group like in propane, butane has two methyl groups, one on each carbon in the Newman projection. This extra methyl group introduces a new kind of interaction, steric strain, and that starts to play a much bigger role in butane's conformational energy. Just like before, butane rotates around its central CC bond, cycling through staggered and eclipsed conformations every 60 degrees. But here's the twist. With two methyl groups, butane doesn't just have two conformations anymore. It actually has four distinct conformations: fully eclipsed, eclipsed, gauche, and anti. Butane has two types of eclipsed conformations and two types of staggered conformations, and each one has a different spatial arrangement. In the fully eclipsed conformation, at 0 degrees, the two methyl groups are lined up directly with each other. This creates maximum torsional strain and significant steric strain, making it the least favorable conformation overall. At 120 degrees, we get another eclipsed conformation, but this time, one of the methyl groups lines up with a hydrogen, not another methyl group. That alignment reduces steric strain compared to the fully eclipsed form, but there's still torsional strain from the overlapping bonds. So while it's a bit better than 0 degrees, it's still not a very stable conformation. In the gauche conformation, at 60 degrees, the two methyl groups are in a staggered position, but they're still pretty close to each other. This setup causes some steric strain, but it's still more stable than any of the eclipsed conformations we've seen. At 180 degrees, we get the anti-conformation. And in this one, the two methyl groups are positioned as far apart as possible. That spacing eliminates steric strain completely, making this the most stable conformation of butane. Now let's compare their energy differences. The fully eclipsed conformation has the highest energy, about 19 kilojoules per mole, and that's because of the strong methyl-methyl repulsion happening when the two bulky groups line up. The eclipsed conformation at 120 degrees has a slightly lower energy, around 16 kilojoules per mole, because this time, a methyl group is eclipsed with a hydrogen, not another methyl group. That means less steric strain and slightly lower energy than the fully eclipsed form. The gauche conformation has an energy of about 3.8 kilojoules per mole, and that comes from the mild steric strain between the two staggered methyl groups that are still pretty close to each other. Finally, the anti-conformation has the lowest energy, sitting at 0 kilojoules per mole, because it completely eliminates steric strain by keeping the two methyl groups as far apart as possible. Looking at the energy graph, we can see the trend even more clearly. Staggered conformations are always lower in energy than eclipsed ones, and the anti-conformation is the most favorable because it minimizes steric strain the most. And that wraps up butane. As we move on to even larger molecules, these effects become even more important, influencing everything from molecular shape to how reactions actually happen. I'll see you in the next lesson.